Hi, welcome back to the lecture series on metric space and topology. In the last lecture, we discussed something called compactness of general topological spaces. In general topological setup. But I promised you that I will give some more overview on a special kind of topological spaces which are metrizable, right? Metrizable topological spaces. So because in case of metrizable topological spaces, it is easy to visualize the open sets. In fact, to visualize the basic open set, which are basically the basic open balls, right? So there, of course, it is most obvious to expect that the properties of compactness or connectedness should satisfy some more beautiful properties other than which is not present in general setup. So in this lecture, we are going to discuss only about those kind of things. So let us begin with our discussion today. So today's topic is basically compactness of metrizable metric spaces. Okay. So just to recall that, suppose we have x comma d. It's a metric space. So if it is a metric space, we can induce a topology. Tau d is basically set of all UV subset of x such that for each, or say for every small x belongs to U, there exists epsilon x belongs to real number which is strictly larger than 0 such that B epsilon x centered at x, this particular ball, is completely inside U. Means basically these are the open sets in as the definition of metric spaces. Okay, so these are the open sets. So as a most convenient metric space, we can think about R equipped with normal equivalent topology. Okay, so just go back to your basic course on analysis, which is real analysis 1, I think. So is real analysis, we had a very beautiful property, something called Bolzano-Weierstrass theorem. Okay, so what does this theorem says? That suppose X is subset of R which is closed and bounded. Okay, then let A is subset of X and A is infinite, then A must have a limit point in X. Okay, this is how one can define that. Limit point means, just to recall that let's say there exists certain small x naught belongs to capital X such that for all epsilon belongs to real number, epsilon larger than 0, there exists certain y belongs to B epsilon of x naught such that y belongs to A and y is different from x naught. Okay, so this is a Bolzano-Weierstrass property, which is a very beautiful and useful theorem, which is a very useful theorem in general analysis too. In fact, this theorem was very helpful. In fact, it has another conversion that every sequence in real line, which is every bounded sequence in real line, has a convergence subsequence. In fact, we will come to this particular property later. It is basically another analogous statement of this. So remember that this particular property, that any infinite subset, suppose any infinite subset of X, suppose a subset of X must have a limit point in X. This particular property, this is known as, up to here, this particular property is known as Bolzano y stress property. Okay, so in general metric spaces, any metric space x comma d, it may not have Bolzano-Weierstrass property. Okay, so in general any metric space may not have any Bolzano-Weierstrass property. Okay, but when a metric space may have Bolzano-Weierstrass property, so that is, for that I need another version of Bolzano-Weierstrass theorem, which is basically known as, I mean, which you are most of you are comfortable with, is something called the sequentially compactness. So what the sequential compactness says, that suppose xn this be any sequence of sequence in metric space x comma d, then x is said to, then yeah, I mean x comma d is a metric space, and then x comma d is said to be sequentially compact if this any sequence xn, this has a convergent subsequence. So means basically that there exists k belongs to there exists a subsequence which is basically of the form x n k belongs to natural number, subsequence of xn, and is convergent. Okay, so this is said to be the then x comma d is said to be sequentially compact. All right, it means any sequence is a convergent subsequence. So the relation between these two properties is Bolzano-Weierstrass property and the sequentially compactness are basically equivalent with each other. So the theorem says that suppose x comma d, this is a metric space, then x comma d, this has Bolzano-Weierstrass property if and only if x comma d is sequentially compact. Okay, so the proof is not very difficult. So let us suppose that x comma d, this is sequentially compact. So if it is sequentially compact, so that means if it considers any sequence, it has a convergent subsequence. So for that case, we may assume that a subset of x, and this is infinite subset. Okay, so we may consider a sequence, let's say xn. Okay, not like that. So xn, just consider the sequence xn. So where each xn belongs to A. So because there are infinitely many in this set, there are infinitely real elements from capital X. So that means we can easily choose such kind of xn. We can easily construct such kind of xn. Okay, so this is how one can define the map. So you can, this particular sequence, this must have a convergent subsequence. So if it has a convergent subsequence, so let us consider that some subsequence is k. This is the convergent subsequence of xn. Okay, assume that this converges at certain x belongs to capital X. So sorry, now you see that as there are infinitely many points in this sequence, so you can easily consider that this particular sequence has infinitely many distinct points. Okay, so as xnk converges these two particular points, so we may consider that B is be a set of all such xnk such that k belongs to natural number, and the limit point of this set is itself small x. Okay, so that means so if we consider, let's say if we consider any open set, or let's say B epsilon x be any real number, so this must this must contain certain xn k1. Okay, in fact there exists certain capital K belongs to natural number such that for all k is larger or equal to capital K, let's say nk larger or equal to capital K, let us fix our choice so that for all nk larger or equal to capital K, all the xnk's are inside this particular ball. Okay, so that means these xnk's are coming from where? These xnk's are coming from this particular set capital H again, because we know that B is subset of A. Okay, so as small x is a limit point of this smaller set, so of course it will limit point of this particular larger set itself. So that means x is limit point of A. Okay, but again conversely, suppose that we assume that x comma d, this has Bolzano-Weierstrass property. So so this implies existence of Bolzano-Weierstrass property. Okay, so if it has a Bolzano-Weierstrass property, so then let we take any xn, n belongs to natural number, be any sequence. Okay, so I have to construct a convergent subsequence. All right, so then this particular set, let's say we consider so that invention, this particular set, this must have a limit point in capital X. Let us call it as x naught. Okay, so that means if we consider any open ball b 1 by n x naught, this must intersect with a, and which is different from x naught. Alright, so there exists at least one x n, let's say, not okay, should I write x? Okay, so for every k, let us write it as every k, because we have already used n, so let us use another notation where k belongs to natural number. There exists x and k belongs to a such that x and k belongs to b 1 by k x naught intersection with a minus singleton x naught. So that means x and k is not same as x naught, and x and k belongs to b 1 by k x naught. Okay, so thus for all k belongs to natural number, for all k belongs to natural number, we have certain x and k's, right? So these x and k's, I can consider a subsequence which is basically of this form. Such x and k's. Okay, so this is a subsequence. So what is my claim now? My claim is that x and k, this converges at x naught. So for every epsilon real number and epsilon larger than 0, there exists n epsilon belongs to natural number such that 1 by n epsilon is strictly less than epsilon. So how it is possible? This is possible by Archimedean property. Okay, this kind of 1 by epsilon is possible, right? So if we consider, so you see, first of all, that suppose we consider this one ball. So for all n larger equals n epsilon, just mean that for the theoretical approach, so then 1 by n, this will imply that 1 by n is less or equals 1 by n of epsilon. Now if we consider, let's say x naught here, so let us take this particular open ball. These are radius of 1 by n epsilon. So for all n larger equals n epsilon, okay, so if we consider any ball which is of radius 1 by n, so you see that the radius, this 1 by n is less than equal to this. So that means if we consider this open ball, that is b 1 by n of x naught, this must be contained this larger open ball, right? Because this particular radius is small. So as the radius is small and the center is fixed, that means the ball of radius 1 by n epsilon, this must contain all the balls of radius 1 by n centered at that particular point x naught for every n larger equal to n epsilon. Okay, so it is really easy to geometrical approach. It is very easy to understand. So that means now as it is there, so now you see that suppose we take n larger equals for any nk, let's say for any okay, not epsilon, say nk, let us write it as nk, because we have chosen here, we have indexed these elements as k, right? So it is nk, yeah. So for all nk less or equals I'm sorry, so for all nks nk is larger equals 1 by nk is larger, sorry, for all nk larger equals n epsilon. Okay, if you consider any ball of radius 1 n epsilon, so of course 1 by nk, this must be lesser equals 1 by n epsilon, right? So you see, now you consider that x and k, this belongs to the ball of radius 1 by nk x naught. So that means this must belongs to b of 1 by n epsilon of x naught. Okay, so that means for all nk larger equals to n epsilon, the distance between x and k comma x naught, this is strictly less than 1 by n epsilon, and 1 by n epsilon is less than epsilon, so this is less than epsilon. So for every epsilon we can have such 1 by n epsilon such that all the elements which is larger than n epsilon, this particular fixed natural number n epsilon is basically very adjacent to x naught. Okay, so this is how you can show that this x and k, this is convergent at x naught. Okay, so basically this gives a both side direction that the existence of Bolzano-Weierstrass property, the existence of Bolzano-Weierstrass property is basically equivalent to the sequential compactness of metric spaces. In fact, this is a theorem. We should let us give it as let us name it with theorem A. We'll get back to here. Okay, after a couple of times we'll get back to here. So now in case of metric spaces, we have found another kind of we have got another kind of compactness, which is sequentially compactness. So one may ask this question that is there any connection between the sequentially compactness and compactness as a topological space? Because if we have a metric space, we can easily induce a matrix topology which is induced from the metric, and as we have a topological space, so it is very easy to talk about very obvious to talk about compactness property over that. So now one may get interested to know whether there is a connection between them or not. So yes, there is a connection in case of matricial topological spaces, sequentially compactness if and only compactness. So we'll prove that, but before that I will make another comment. Let us consider is a theorem B. The first one is theorem A, and this one is theorem B. So what this theorem says that every compact metric spaces, so compact metric spaces means in terms of topology. Okay, this has the Bolzano-Weierstrass property. Basically, similarity that predicts a similarity between sequentially compactness and compactness, because sequentially compactness implies a Bolzano-Weierstrass property. Compactness also implies a Bolzano-Weierstrass property. So suppose you have x comma d. This is a metric space. So from metric space you can have induced topological space x comma tau d. This is induced topological space. Okay, so let's consider that A is subset of X. Okay, this is infinite. This is infinite subset. Okay, now let us assume that A has no limit point. Okay, so that means there exist so therefore each small x belongs to capital X. So you see that we have started with the compact metric space means compact is a topological space with respect to induced topology. So anyway we have to use the compactness property. So what is compact property means? Every open cover has a finite subcover. So that means we have to construct a finite cover, construct an open cover for this metric space in the topology. So that is our approach. So if we consider any small x belongs to capital X, so there exists certain epsilon x belongs to real number and epsilon x larger than 0 such that b epsilon x of small x intersection capital A minus singleton x, this is phi. Okay, so that means there are two possibilities. Once you have this one, so there are two possibilities. One is b epsilon s of small x intersection of A, it is exactly singleton x, or it is phi itself. So b epsilon x of small x intersection with A, it is phi itself. All right, so if you fix any small x of this form, then it is done. Of this kind of formation is there. Okay, so that means to have this particular one, we can restrict this one as b epsilon x of let's say epsilon x of small a of intersection A equal to singleton x. This is true for all x belongs to capital A. Okay, for this it is fine, and this is true if x for all x belongs to capital X minus capital A. Okay, then there is no problem. So now what I can define that we can consider this particular class the set of all b epsilon of x small x means capital X of this kind of form. Okay, this kind of form. Now we will show that this is an open cover for this matrix space small x. So if we have, let's say, small x belongs to capital A, so that means of course small x must belongs to the epsilon of x of small x. This belongs to x, and otherwise it is not. Otherwise, if we consider any small x which is small x belongs to x minus a, so that means of course here also x belongs to that particular okay, x1 belongs to b epsilon x1 of x1. Okay, here it belongs to. So that means we can cover this capital X with small x belongs to capital X b epsilon of x small x. So you note that we don't need the property that it may be to any two open balls may overlap with each other at certain region, up to certain region, but it of course both should not be any two particular open balls should not be exactly same. Okay, so this is implies that this is an open cover for capital X. Now, and of course it is with respect to the basic induced topology tau d. So as it is open cover for this x and x comma tau d, this is compactness. So by compactness there exists, we can write x to be as b epsilon x1 small x1 union up to b epsilon xn to xn. Okay, So it's a compact space. So this is a finite subcore basically. So this is subcover for X, capital X. Okay. So then we may consider capital A to be as x1 up to xn. Alright, because this is my, it has to be, because anyway each xi's are coming from, each xi's are coming from capital A as per the construct, as per the definition of this map. Because I mean, either maybe x belongs to capital A if we consider only, if we consider take any point small x which is on capital A, then this intersection has any singleton point. So the small x size, so then I mean we have that A subset of X. So that means let us consider any small, and it is infinite, right? So of course capital A is non-empty. So if we take any small a belongs to capital A, okay, so that means small a must belongs to at least one of these B epsilon of x1 of x1. Okay, at least one of these x1 has to be there, small x. So that means B epsilon of x1 of small x1 intersection with capital A, let small a is not equal to x1. Let us assume this one. For instance, assume. So now singleton small x1, this has to be, I mean this must be non-empty, because this particular one must contain this particular small a, right? But we have assumed that always this is true. So that means it is obviously each small a must be same as x1. So thus for every small a we can have certain x1. So so of course a small a must be x1, well, at least one. Now we may consider that let's say small b belongs to capital A, such that small b belongs to certain another b epsilon of x2 of x2. By the way, so then obviously b must be same as x2. By the way, so is it possible that if we take any two different element a and b and these are in the same open ball of this form? It is not possible, right? Because then again a and b both will be same as small x1. So that means for every arbitrarily chosen small a and small, distinct small a and small b, I must get certain, I will stop up to nth step, right? So there are certain a1, let's say a, b and so on after nth stage. Let's say it is a1, let us take it as a2, and after nth stage we will get an is same as xn. I'm sorry, not this one, this is a2. A2. So after n stage it will stop. So that means it is obvious that A is basically consisted of, basically nothing, not consisted, it is consisted of only these finitely many elements, which is x1 up to xn, x1, x2 up to xn. These finitely many elements are there. Okay, so that means A is finite, but this is contradiction because we have assumed that A is infinite. So by contradiction, hence A must have a limit point. This is by contradiction. Okay. All right. So that means we have got three kind of things. One is basically Bolzano-Weierstrass property. Another one is sequentially compactness. Another one is compact as topological space. So from Bolzano-Weierstrass property to sequentially compactness, there is a both side reaction equivalence. Okay. From compactness to Bolzano-Weierstrass property, there is one side equivalence. Now, if we can prove that sequentially compactness implies compactness, then basically this particular diagram is commutative. Why? Because suppose we have a Bolzano-Weierstrass property. Okay, so let us take, we have a Bolzano-Weierstrass property. So Bolzano-Weierstrass property implies there is compactness via this direction, and compactness will imply compactness via this direction. Okay, again, suppose we have a compact metric space, compact is topological space, induced topological space. So from this direction, this has Bolzano-Weierstrass property, and via this direction it has sequentially compactness property. Okay, again, if we have sequentially compactness, so it will help Bolzano-Weierstrass property, and it will have sequentially compactness as a topological space. So that means this particular one is actually needed to make this diagram commutative. Okay, from any direction, that is doesn't matter. So before proving that, we need a very important topic related to this proof is something called the Lebesgue number. I think it is LEBES. Yeah, it's the Lebesgue number. So what is the Lebesgue number? The definition says that, so suppose we consider that x comma d, this is a metric space. So the induced topological space is x comma tau d, is the induced topological space. Now let us consider an open cover. This is induced topological space. Let us consider an open cover Gi is same as capital X. Okay, a positive real number small a belongs to R larger than 0 is said to be a Lebesgue number for this open cover Gi if for any a subset of X, whenever the diameter of A is less than small a, that will imply that A is sitting inside at least one Gi for at least one small I belongs to capital I. So basically that means that suppose we have a topological space like this, okay, so we have, let's say these are the open covers, open balls of this form, open cover basically. Just ignore the outside part, okay? So these are the open covers. So let us assume we have another certain subset. This is a subset capital A So let's say small a belongs to real number, comma smallest larger than 0. This is said to be a positive Lebesgue number. This is associated with this particular open cover. If we have any d of, let's say this diameter of this set is less than s. What is diameter of this set? Is supremum of all d of a comma b such that a comma b belongs to capital A. The supremum of this map is strictly less than capital A. That means this, instead of spreading out in the two or more open covers or open basic open covers, or let's say open cover set, it is sitting inside at least one open cover. So that means there exists certain at least one GI in which it is sitting inside. Okay, so A is exactly inside this thing. Means it is not spreading throughout some more open set included in the open cover. Okay, it is sitting inside at least one GIs. Now if J is sitting in another open set, then it is sitting inside there also. Okay, so or it may be sitting inside intersection of any two open set included in the open cover collection of the open covers. Okay, so means it is basically seated, maybe it may sit here or it may sit at least one of them, whatever, but it is exactly inside at entire GI. At least one GI is there which is containing this capital A entirely. This is the definition of positive Lebesgue number. Remember that if we change this open cover GI, then the positive Lebesgue number will always get changed. Okay, so every open cover has a fixed Lebesgue number. In fact, that is our goal in the next proof. So that every open sequentially, it is possible in case of only sequentially compactness, because we are trying to prove sequentially compactness in implies compactness. So this is particular property is related to sequentially compactness. Alright, so theorem, I have already stated the statement. So the theorem is that suppose x comma d is sequentially compact, then every open cover for x comma d has a positive Lebesgue number. Okay, I'm sorry. Okay. So let us assume that we have a x comma d. This is sequentially compact. So let us consider an open cover GI. This is the open cover for this x. So my claim is that it is a positive Lebesgue number. So assume that there doesn't exist any capital subset of x such that capital is inside G of I for any small I belongs to capital A. Okay, so then we can consider the class such that A is subset of x and A is not subset of Gi for any I small against capital. Okay, so in fact it is a set, all these are all subsets of X, that is fine. So then we consider that A dash to be the infimum of the diameter of A such that capital A belongs to this collection. Okay. So clearly this may be A dash is of course larger equal to 0 and maybe infinity it's as well, but it has to be run over the positive real line. So you assume that A dash is 0. So if A dash is 0, now let us consider any capital A belongs to this collection. So of course capital A must be subset of X. So that means capital A, this must be union of all such Gi's. Okay. So let capital A singleton set. So then small x must be at least one Gi or at least one I. So then A must be subset of Gi, but this is not possible. But not possible. So that means capital A, cardinally capital is to be larger equal to 2, at least 2. Okay. So now we may see that we have started with a sequential compactness. So we have to use sequentially compactness. Anyway, you have to construct a sequence in this capital X. So for each n belongs to natural number, so as 1 by n is larger or equal to 0, in fact is strictly larger than 0, so this particular wall 1 by n so yeah, I mean as it is larger than 0, so this cannot be a lower bound of A. Okay, so that means I mean cannot be lower bound of this infimum set, lower bound of this set D of A such that A belongs to A, collection of all these sets. Okay, so that means there exists some dA1 I mean there is certain such some A1 which is subset of let's say A1 belongs to this collection such that 1 by n is less than 1 by n is larger than D of A1. Okay, let's say certain an instead of A1 there is an, because it depends on the choice of small n, right? So now for each small n, and in fact this is non-empty, so for each small n we can consider xn in natural number where each xn this belongs to an. Okay, we can assume that suppose we have chosen to another n1 comma n2 natural numbers such that both are different, n1 is not equal to same as n2. If these two are different, then an1 and an2, this must be different. I mean, you can consider that these two are different because there are infinitely many choices for me, right? So that means this particular sequence xn, these are basically consisted of exactly one element from each an. Okay, because for me there are infinitely many choices of 1 by n. Okay, and each xn are coming from an. So if there are any two particular elements, we can take at least exactly one from those particular set. And there are infinitely many an's options are there. So we may assume that each xn is coming from exactly once from each an. I mean, every an contributes once to this particular sequence. So as it is a sequence, so and you have a sequentially compact metric space, so this must have a convergent subsequence. So as it is a convergent subsequence, so that means let us assume that yn ynm, not y is x, it is enough to work with x. This is the convergent subsequence. So x nm, this is convergent at small x, not, let's say. Okay. So as small x naught belongs to capital X, so that means small x naught must belongs to this entire union of gi's. So small x naught must belongs to at least one gi. Okay. Now this is open set x comma d. So that means there exists r naught belongs to real numbers greater than 0 such that b r naught x naught is inside gi. Okay. Now if we consider that b r naught by 2 x naught which is inside b r naught of x naught inside gi. Okay. Now for r naught larger than 0, there exists an r naught, let's say it depends on r naught, this belongs to natural number such that for all n k's larger than or equal to n r naught such that we have x n k, so in m, sorry, we have defined x in m, right? Yeah, x in m, this belongs to b r naught by 2 x naught. Okay, so by Archimedean property again, by Archimedean property, there exists at least one small k belongs to natural number such that 1 by k is strictly less than r naught by 2. So that means basically we are applying Archimedean property with 2 and r naught. Okay. So then, so you see that we have two natural numbers. One is small k here, and another one is in r naught here. Okay. So we may consider that n naught belongs to natural number such that n naught equal to is larger equal to the maximum of n r naught and small k. Okay, so that means 1 by n naught, this is strictly less than r naught by 2. Okay, because 1 by n naught is less than equal to, because n naught is less than k, so 1 by n naught is less than 1 by k. So 1 by k, and it is itself less than equal to this, so 1 by naught has to be less than equal to r naught by 2. So that means this diameter of b n naught, this is less than 1 by n naught less than r naught by 2, right? So that means such b n naught will exist in r naught by 2. Okay, because as per the not b, let us as a, yeah, because as we have defined this 1 by n, because by this property that 1 by n, because 1 by n naught is again not a lower bound of this set, so 1 by n must be larger equal to certain d of a n naught from this property. So let us name this set star. So it is from star. Okay, so that means now you see that d of a n naught is less than equal to r naught by 2. So that means b n naught, a n naught, which is exactly inside b of r naught by 2 of x, which is inside g I naught. So why this is true? Because because a n naught intersection with b of r naught by 2 intersection is not equal to phi, right? So that means there exists because is x n naught, this has to be inside b, this has to be inside a n naught intersection with b r naught by 2 of x. Okay, and d of a n naught is less than r naught by 2. So combining these two properties, you can easily show that all the elements of a n naught if we take any two particular points in between a n naught small a, which is from a n naught, then by applying the this particular r naught, yes, now it is fine, sorry. So if we consider any over small a belongs to a n naught, okay, then the distance between a comma x is basically less or equals to the distance between it is distance between a comma b plus distance between b comma, not b, it is a comma this particular element x n naught, x n naught plus d of x n naught comma x. So this particular one is less than equal to r by 2. So this particular one is less than 1 by n naught, and this particular one is less than r naught by 2. And 1 by n naught is again less than equal to r naught by 2. R naught by 2. Then the entire one is r naught less than r naught. So that means this small a has to be inside this b r naught x. Okay, so that means once it is, this is inside a n naught, and a n again it is inside b and b a r naught of x for every small a. That means this entire one is subset of this, and that means that is this a n naught is inside g I naught. So we get that, but this is not possible, right? This particular is not possible because a n naught, this has been chosen from this curly set that we have defined in the starting. So hence a n naught should not belongs to a. This is the contradiction. So what was our assumption? That small a must not be 0. So small a must be strictly larger than 0. Okay. So small a larger than 0. Now there are again another option. So small a, it may be less or equal to plus infinity, but we have got that it is strictly larger than 0. Okay. So let small a is strictly positive. It is finite. Let's say small a is finite. Okay. So if small a is finite, then for any capital A subset of X, we have the diameter of A. This is less than small, right? So that means capital A, this also belongs to this set, because if capital A should belongs to this, so A is greatest lower bound, so small a has to be less or equal to this. Okay, so for any set, if this is true, then it has not be there, it should not be there. Okay, so that means for each so that means that there exists at least one small I belongs to capital I, such that capital A is inside Gi, because since it is not in this set, it must be inside certain Gi as per the definition of this class. Okay, so again, if we consider that, let's say small a is infinite, so again, if small a is infinite, then we can choose any smaller. So you can choose any a1 belongs to real number, larger than any real number. So if it is any real number, so okay, let us move it in the next page. Yeah. So let us, next case is, suppose A is strictly infinite. So then choose any, let's say delta belongs to real number strictly larger than 0, any real number. Okay, so then if we choose any B subset of X such that the diameter of this set is less than delta, so that means what? It is equivalent plus infinity, right? So that means B, so the diameter of B is strictly less than small a itself, so that means B must not belongs to this class, so that means B is inside certain Gj. Okay, so then small delta, this will be the Lebesgue number for Gi. Oh, I forgot to mention here, in that if A is finite, then this will be the positive Lebesgue number. Okay, this is how one can construct this map. All right, so if we have any sequentially compact metric space, then any open cover, it has a positive Lebesgue number associated with a positive Lebesgue number. All right, so this completes the proof. Okay, now we will give some two basic definitions and one very important remark, and after that we will start with the sequentially compact metric space, but maybe we'll stop just giving the remark and epsilon definitions, because I will like to you to brush up all these previous discussions. In the next class we will discuss the main lemma and complete the proof of complete the diagram of this commutative diagram. Okay, diagram. this particular commutative diagram. All right. So there is something called epsilon net. So what is an epsilon net? Suppose x comma d is a metric space. So if it is a metric space, then suppose we have epsilon belongs to real number, epsilon larger than 0, it is given, and suppose we have a subset of x. This is said to be epsilon net of x if a is finite and capital X is basically union of all small a belongs to capital A, p epsilon of small a. So that means this particular basic open set this can be covered with some finitely many open balls of same size. Okay, this can be covered with some finitely many open balls of same size. Alright, so this is said to be an open epsilon net. And if you have a metric space x comma d which has an epsilon net, for each epsilon belongs to real number which is larger than 0, then x comma d is said to be totally bounded metric space. Okay, so these two are very important and interesting notes that one should make before going to the proof of sequentially compactness. So let us stop it here. Please revisit all these stuffs we have discussed today, and before coming to the next class, make sure that you are comfortable with compactness and sequentially compactness, mostly because in the next class we are going to deal with all those two things, because we are just going to make the bridge in between those two pillars. So I'll start, I will state the theorem and prove that particular bridge in the next class. Okay, so let's call it a day, and thank you very much for today.